Okay, again, as long as we're in this chapter, you have to pretend like you don't know what a derivative is and you don't know what the rules for taking derivatives are, because we're going to start talking about the rates of change and tangent lines, and this is setting up the definition of a derivative, which we're going to do next Tuesday, I mean. So you have to temporarily suspend your memory about what you remember. So we're going to talk about in 1.4, we'll review what it means to be a tangent line, what it means to find the slope of a curve, the difference between instantaneous and average rate of change, and then something new called sensitivity, which is just a new vocabulary word, but it still means the instantaneous rate of change. So it's an equivalent idea, it's just a new vocabulary word to refer to that. All right, so average rate of change by definition, it's the amount of change, oh, I don't like yellow. Okay, the amount of change, which is delta y, divided by the length of the interval, which is delta x. And so the average rate of change is also thought of as the slope. And so this is delta y over delta x, or we know it as y2 minus y1 over x2 minus x1, or we know it as f of b minus f of a over b minus a. So all of those things are equivalent, and this is defined as the average rate of change between two endpoints on an interval, okay, from one endpoint to the other. So just so that you know that it's a definition of average. And this is getting us into the differential of y divided by the differential of x, which we know we're getting close to thinking about derivatives. Okay, we're just setting the stage for that. Okay. So a quick sample of finding the average rate of change over a closed interval. So you would want to know what the y values at the endpoints of the interval were. So what is f of negative 2? So you're looking at 2 times negative 2 squared minus 3 times negative 2 plus 7. And then the other one would be 2 times 4 squared minus 3 times 4 also plus 7. So we're looking at 8 plus 6 plus 7. So 14 plus 7, we're looking at 21. And then the other one is 32 minus 12, that's 20, plus 7, so we're looking at 27. So the average rate of change would be the change in y's over the change in x's. So 27 minus 21 over 4 minus negative 2. So 6 over 6, the average rate of change over the interval is 1. So no calculus required, just some quick math on that. So this completely relates to the slope of a line. If you're going to look at that visually, this curve here, a parabola going from 2x squared minus 3x plus 7 from negative 2 to 4, we're looking at the pieces of a parabola here. So the parabola itself, this is not drawn to scale, by the way. The parabola itself is totally curved, but we are finding the slope of the line that connects those 2 points. And the closer those 2 points get to each other, the straighter that curve appears to be. Okay, the key word being appear. We know a curve is not straight, but the more we zoom in to a curve, okay, look at those pixels, the straighter it appears to get. And that would be the farther we zoom in or the closer the points are that we get to each other. So in calculus, we often want to define the rate at which the value of a function is changing with respect to x. We define that to be the slope of the tangent line. And this tangent line is a straight line attached to a curve. And so the problem is we only have 1 point to work with instead of the definition of slope, which requires 2 points. So we make our points super close to one another. We kind of get around that by, if I want to find the slope here at x1, y1, then I zoom way, way, way in, and I find a second point as close to that point as possible, x2, y2, where the difference between those is approaching 0. So it's so close to each other that you can hardly tell the difference. And so what we end up deciding to do is, instead of renaming it something new, we say this is x1 plus a tiny little bit called h. And then the y value would be y1 also plus a tiny little bit. A better way to write that would be, what would the function value be with x1 with a little bit of h added to it? So that's our y1 value. And we find the slope between those 2 points. And so instead of using y1, I'm going to change that to f of x sub 1. So this would be the y value, and then the next y value moving a tiny bit away. So if we find the slope between those 2 distinct points, but those 2 distinct points are very close to each other, the slope would be delta y divided by delta x. So it would be f of x1 plus h minus f of x sub 1 over the second x, which is x1 plus h, minus the original x. And we clean that up. And we clean it up to the point where the denominator is just h. H representing the difference between the 2 x values, and we want that to be so small that the value of h is approaching 0, and that will give me the slope value at the curve. All right, so unmute yourselves. Who remembers which mathematician developed this from last year? Anybody?
Isaac Newton.
Yes, this was Isaac Newton's definition. He was competing with Leibniz. Leibniz came up with a very similar idea, but he notated it differently. His notation was different. This is Newton's definition for the slope of a line, and then he named it the derivative later, but this is his definition for the slope of a curve. All right, so here's a better drawing of what I was trying to demonstrate. This drawing shows the original point A here and the second point A plus H. And according to this drawing, they're fairly far apart, at least visually. And what we want to imagine is that the point is moving closer and closer and closer and closer along the curve until the moment when those 2 points are simultaneous, or at least so close together we can't tell the difference between them. All right, here you go. The slope of the curve is defined this way. Okay, we give credit to this definition to Sir Isaac Newton. And he called it the tangent line to the curve. All right, so to create a tangent line, you need 2 things. You need the point and you need a slope. And we will create then the point slope equation. So the point would be x1, y1. The slope would be whatever you're going to find from Newton's definition. And then you write the tangent line this way. And here's your equation for a tangent line. Please remember, you don't have to simplify that. You don't have to distribute. You don't have to clean it up. You may if you like, but you do not have to simplify a tangent line. You can leave it in its point slope format. So here are all the ways you can be referring to the slope. The slope of a curve, the slope of f of x at a single point, the slope of a tangent line, the instantaneous rate of change, Newton's definition, which is number 4, and Leibniz's definition, which is number 5. All of these things have the same meaning. Okay, it's just you have to get used to the language. And then we're going to add number 6, sensitivity. How sensitive is a real life function at that particular point? And I really want you to think about this, like, think about when you want to ask your parents for something and you want to make sure that they're in a pretty prime good mood, because if someone is extremely quote unquote sensitive, the littlest thing just sets them off and they explode and they lose their temper. Okay, that would be being sensitive to something where the smallest thing just sort of sets you off. Or you could have somebody that's just a real even keel, and even if something totally changes around them, they don't really change very much. I feel like Mr. Taminga's kind of that way. He's just real level and even tempered, and he's not gonna like fly off the handle for anything. So his sensitivity is low, whereas somebody else might have a really high sensitivity because they're gonna, freak out at the smallest little thing. All right, so let's talk about how you're gonna show your work for this. I know that most of you remember how to do your derivative already, but for now I need you to prove to me that you know how to define the derivative. So if you're supposed to find a tangent line, this is what you'll need to show me. You'll need to show me the point, and I'm asking you to find it at -1, so that would be the point -1 comma, and then 3 is the y value. And then for the slope, you're gonna have to show it that at least you know how the definition works. Because it's one thing to know all the rules, but you still have to know why the rules work the way they do. And so we'll be looking for the definition of the slope. So we wanna take x plus a little bit, x plus h squared plus 2. And we wanna subtract from that the original function, x squared plus 2. So this is the function, the second y value minus the first y value, all over h. And as long as we're doing the algebra, we're keeping our limit notation proper. So we'll have x squared plus 2xh plus h squared plus 2, so I've just expanded the FOIL, minus x squared minus 2, the whole thing over h. And so I want to simplify that. The squared terms cancel each other out. The 2's cancel each other out, leaving me with 2xh and h squared, which have the common factor of h. So I can take h out, leaving me with 2x plus h, still over h. Once I've factored, the h terms reduce, and I'm left with still the limit as h approaches 0 of parentheses 2x plus h, which is going to be 2x when h is 0. So the slope at the x value of of -1 is going to be -2. So now I can write the equation of I found my slope of the curve, and now my tangent line can be written as y minus 3 equals -2 x plus 1. And you don't have to simplify that. That is the equation of the tangent line. And here's a visual of how that looks. You have the parabola, and you have the point -1, 3. And at that point, the curve of the parabola and the line share the same slope and are essentially the same at that tangent point. The normal would be creating a perpendicular line. The word normal means perpendicular. So if we were going to come back here and we wanted to create a perpendicular line at that point, then our perpendicular line would be y minus 3. The perpendicular slope is the negative reciprocal, so that would be positive 1/2, and then x plus 1. So there's my normal line. Okay. Oh, here we go. There's your normal line. I put a picture in later.
Ms. Pfeiffer, do
Yeah.
you mind doing a slope one with Leibniz as well?
Oh, sure. I'm just going to do it on this this slide because I haven't used it yet. So we want the limit of f of b minus f of a over b minus a as b approaches a. Okay, Leibniz has to do with factoring. So I want b squared plus 2 minus a squared minus 2 all over b minus a. So you can see the 2's reduce away, and then there's always factoring to be done. So I'm left with b squared minus a squared over b minus a, which is factorable. So in Leibniz, with polynomials, that will always happen. Well, you'll have b minus a over b plus a over b minus a. So that can totally reduce. So you'll have the limit as b approaches a of b plus a. And so since b is approaching a, we'll have a plus a. So 2a is the value of Leibniz's definition, and at the point -1, that would still have a slope of -1. All right, does that help you remember that? But it's always going to be factoring. You factor out a b minus a. Okay, another way this also applies to velocity. So when they ask about velocity, they're asking about the slope of the curve. So it's the same, it's new language to the same topic. So just so that you are understanding that. And then sensitivity. Okay, we've talked about that a little bit. So some examples, I gave you the example of somebody's emotions, but some other real life examples. If you talking about being sensitive to rainfall, you know, if you think about, I think about flash floods. You know, if there's no water, no rain, and then all of a sudden we have a little bit of rain, boom, there's a huge sensitivity to that, and we could have a flash flood in that area. Or if you look at a drug, if someone is running a fever, you give them a small amount of a drug, and then that can have an impact on reducing the fever. So sometimes a little thing can have a big impact. That's how sensitivity is going to work. The steeper the curve, the more sensitive it is. Okay, a greater sensitivity to something. But again, if they're asking, the question asks you how sensitive is it, they're just asking you for the slope of the curve at that point of the function. So it's basically, I just wanted you to know that there's some new language now. This is added by the AP curriculum from last year till this year. It's just a small change, small addition. Okay, so now we've got all the ways that you can refer to the slope of a curve. We've added on to their instantaneous, velocity, and sensitivity. And that's it. So that covers your review of chapter 1.